Assalamualaikum. I be to my lecturer, Dr. Shazah, and today my group going to present a reactor separator system for the conversion of palm oil resources for the integrated project assignment. For the table of content, the first one will be the introduction and objective, and then the second one is the design of reaction process system for conversion of palm into biodiesel in stage 2, and then my team members will be explain more in terms of this chapter, and the third one is the conclusion, and then the last one will be the reference. So this is our team members. The first one is NURSHARISHA ADILAH, NAJIHAH MAZLAN, SHAFIQAH ELIDAH, and NURULFARAH ADILAH, and all of us are from applied chemistry. First is the introduction of the case study. Nowadays, the level of dependency on petroleum as one of the energy and fuel source is very high. However, the petroleum feedstock are depleted day by day, and almost 90% of the petroleum are used for the transportation. Therefore, one of the ways to sustain the fuel source for the transportation is by producing biodiesel blend fuel, also known as the B20, in which 20% are from the biodiesel and 80% is from the petroleum. So in this project, we are going to propose a design on a reactor separator system to undergo the trans-esterifications in order to process or convert the palm oil fruit into the biodiesel. The objective for this project, the first one is to design a palm oil biodiesel reactor separator system that achieve high conversion of product. And then the second one is to create a sustainable reactor system for the biodiesel production. And the last one is to generate high quality palm oil biodiesel for the blends with the petroleum for the transportation sector.
Moving on to the next part, which is process flow diagram in producing biodiesel production. So here is the illustration of our process flow diagram, in which the mini pilot plant for the biodiesel production is carried out in 3 plug flow reactors with recycled shrimp under trans-esteration process due to rapid reaction rate and high yields. So the type of catalyst used is throughout this reaction is homogeneous basic, which is sodium hydroxide catalyst, and the solvent used are the triolene and ethanol to represent oil and alcohol respectively. As we can see there, the catalyst was included in the alcohol stream first, then mixing them with the oil stream, which is the triolene, before feeding the first reactor. And at the same time, the recycled stream will also added between the first and second reactors that could assume different values. And as a result, the product stream correspond to ester, sodium hydroxide, glycerin, and unreacted oil and alcohol. Oh, not to mention, the PFD of biodiesel production is carried out with the splitter and mixer to permit the reaction of the final products to occur and could benefit by minimizing the cost of industrial project later on. Thus, the performance equation that need to be used for the reactor must be estimated in order to get the correct size of chemical reactors. This is the operating condition that we use when we want to design our process flow diagram by using the symmetry software. We can see that these are the parameters that we found through our research and our literature review.
So let's go to the calculation part to know either that our design have high conversion and high performance of the reaction.
For the assumptions that will be applied for the calculation part, the reactor is operated at continuous steady state with the phase liquid reaction where the density is constant, so the volumetric flow rate at the inlet and the outlet are in equal state. The reaction is carried out in a non-isothermal condition where the work term is negligible and the specific heat capacity is constant, where the summation of the energy is negligible compared to the enthalpy.
So firstly, we need to focus on the chemical equation to produce oil, which is 3 mole of alcohol react with 1 mole triglyceride to produce ester and also glycerol with the presence of catalyst. This chemical equation can be expressed by this right law, and also we can calculate the concentration of triglyceride and alcohol by using this equation. So to know more detail regarding the design to produce the oil, we can construct the stoichiometric table trans-esterification with the flow rate of the triglyceride and alcohol be mentioned in the reference, which is 1 to 3.1 mole per second, and also the conversion of the triglyceride is 0.5 to 4. The transesterification limiting reaction is the triglyceride, so we focus on the conversion of TG. So here we can calculate and construct the stoichiometry table transesterification. So from here we can know the reaction order of the design by calculate the concentration for non-isothermal and negligible pressure of the reaction. So we can get the data from the reference, which is the conversion of triglyceride against time, and we include in the equation given here. After that, we can calculate the sigma YA naught times delta, and from in this reaction the delta is 0 and the sigma is also 0. We can also acquire the residence times and conversion of triglyceride at a particular time.
To find the reaction order for this calculation, we are using the mole balance equation so that we can derive it into the rate. So, for the zero order equation, we are integrated the calculation to becoming Ca equals to Ca naught minus Kat. And for the first order equation, we will integrate to becoming into ln Ca naught over Ca equals to Kt. Based on previous calculation for zero order reaction, which we have been integrate into Ca is equals to Ca naught minus Kat, which represent for y is Ca and x is for time. With the gas alpha value equals to 0, we have plot the graph which is Ca is versus to time. In this graph, we are shown that the plot is not in a linear form, thus it is not a zero order reaction. As for the first order of reaction, we can use the ln Ca naught over Ca is equals to Kt, while the y is represented as the ln Ca naught over Ca and the x is for the time. In this case, we are guessing the alpha value is becoming into 1, and from the plotted graph, as we can see here, it is ln Ca naught over Ca versus with the time. From here, we can see it is in a linear form. Thus, it is shown to be proven as the first order of reaction. And from here as well, we can identify the constant rate, which is 0.0304, which is the m value. Thus, in order for us to get the rate of the formation of the product, we need to find the highest value of the conversion in triglycerides, and we can multiply with the m value just in previous slide, and there we can get the rate of formation of products is equal to 9.24 times 10 to the power of negative 4.
Here I will explain the strategy to enhance our biodiesel production yield as well as minimizing any byproducts formation. There are three kinds of factors that need to be considered throughout the PFD. First, we look at the recycle ratio. Second, the minimal residence. Last but not least is the implementation of esterification transesterification process throughout our design. First factor is the recycle ratio, which needs to be 0 because recycle ratio will affect the selectivity and yield of biodiesel, where the effect of rising in recycle ratio was to reduce the chemical conversion of our biodiesel production. In this context, high conversion in PFRs can be achieved with minimal residence time at recycle ratio equal to 0 in order to obtain almost to 98% conversion into the biodiesel products, mainly ester. The statement is supported with the 3-mat illustration created in MATLAB by Silva et al. 2017 as illustrated there, in which undesirable condition for the biodiesel condition in a PFR is shown in the light area up on the left side, and it happened due to extended residence time required for high ester conversion. Last but not least is the implementation of esterification, transesterification process in yielding high production of biodiesel. So what are the strategies to minimize this side reaction? Let's move on to the next slide. To cater this problem, we need to implement the presence of alkali catalyst in excess form. Why? Because the usage of alkali catalyst can promote an efficient operation and its mass fraction ratio relating to the feeding oil according to Silva et al. 2017.
For this part, I will explain about the limitation that has been used in this reactor and the system. For the limitations of the selected reactor and the system, such in this case we are using the PFR, it could increase a recycle ratio followed with a decreased conversion, and a longer residence times will achieve a high recycle ratios and the conversions will be achieved, but it could also will cause an increase for the cost of the process where it requires a larger units of construction, such as 9 PFRs of the same value are required to achieve 98% of conversion into esters. In addition to that, the reaction rate is faster at a higher temperature, but as the reaction proceeds with time, the conversion will remain constant. As this case study by Nureddini et al. In 1997, a higher temperature will favor backward reaction.
As a conclusion, the PFR reactors are very convenient to achieve the high product conversion since the reaction can occur simultaneously with the product generation, in which different with other reactors at certain conditions. And then the second one is the assumptions are very crucial to ensure the process occur very well in the reactor and can yield high conversions of product. And then the last one is the limitations of the reactor system are very important to be analyzed in order to prevent any issues and problems that might be occur in the system. I think that's all from us. Thank you.